Let's go ahead and learn the cover-up method for finding a partial fraction decomposition. So this is going to assume that you have already learned some of the other more traditional methods of finding partial fraction decompositions. We are going to weave in some of those other strategies during this process. So here we have the rational expression x minus 1 all over the quantity x minus 3 times the quantity x plus 2. The denominator's already factored, that's nice. It factors to distinct linear factors, so each of those is going to get its own partial fraction. And what we traditionally do is we put a generic constant like a over the factor x minus 3 plus a generic constant, let's call it b, over the quantity x plus 2. And we're in search of a and b. So what we're going to do in this cover-up method is we're going to look at one of these partial fractions, we're going to look at its denominator, and we're going to try to think about what value would make the denominator equal 0 when substituted into x. So this is really nice. If I substitute in 3, 3 minus 3 is 0. Basically, we're just setting this equal to 0 in our head. So if I set x minus 3 equal to 0, I would add the 3 to the other side, get x equals 3. So I'm going to hold on to that value in my head of positive 3. And then here comes the cover-up part. I'm going to go back up to this expression here, the rational expression with a factor denominator, and I'm going to cover up the factor x minus 3. If I were doing this on paper, I could cover it up with my finger. Here, what I'm going to do is just sort of scratch it out. And so now I take that value of 3 that I'm holding onto in my head and I substitute it into any remaining x's in the rational expression. And the idea is that we want to do this in our head. Because I'm just going over it for potentially the first time, I'm going to show this arithmetic here. So if I substitute in 3, I have 3 minus 1 over 3 plus 2. So I get 2 over 5. So what we just found is the value of a. So the value that goes above that factor that we covered up, x minus 3. So we have our first partial fraction as 2/5 over x minus 3. And then we can do the same process for finding the value above x plus 2. So I'm going to think about what's going to zero this out. So if I set this equal to 0, I'm going to get out negative 2. Negative 2 plus 2 is 0. So I'll hold on to negative 2 in my head, come up to the original rational expression that's factored, cover up x plus 2, and then substitute in negative 2 into each remaining x. So if I do that, I'm going to get negative 2 minus 1 over negative 2 minus 3. So we're going to have negative 3 over negative 5. That's going to give me positive 3/5. So positive 3/5 goes above x plus 2. And there is our partial fraction decomposition using the cover-up method. So again, ideally, we are going to do this work in our head because this is supposed to be a shortcut method. And in fact, we can skip this step here, really, of writing a generic constant a and generic constant b because we can dive right into finding those values. And we'll see that in the next example. Before we jump into the next example, I just want to briefly show why the cover-up method works. So in that first example, we had x minus 1 all over the quantity x minus 3 times x plus 2, and we said the two partial fractions were going to be a over x minus 3 plus b over x plus 2. Well, that means that adding these back together better get us back to the original rational expression. So what we really need is common denominators, which is the entire quantity x minus 3, x plus 2, so we multiply the top and bottom here by x plus 2, because that's like multiplying by 1, multiply the top and bottom here by x minus 3, and so we end up getting one rational expression with this as my numerator. So it's kind of like cross multiplying, right? A times x plus 2 plus b times x minus 3. So this numerator, x minus 1, must equal this numerator over here. That's that primary equation that we use to move forward with finding the missing values. So the traditional method involves creating a system of equations, but one of the shortcut methods involves looking at this expression and thinking about what zeroes out one of the terms on the right-hand side. And so over here, if we think about what's going to zero out x plus 2, well, that's going to be -2. And so what we do is we go ahead and let x equal -2. So I just want us to see what's happening. If I let x equal -2, we're going to have -2 minus 1 is equal to, okay, well, this whole thing becomes 0. -2 plus 2 is 0. This whole term is gone. And then I have b, and then times the quantity -2 minus 3. So I'm in search of b, so I'm going to divide by -2 minus 3. So I have -2 minus 1 divided by -2 minus 3 is equal to b. So I'm writing it like this so that we can see how it's really just x minus 1 with a -2 plugged in, and then x minus 3 with a -2 plugged in, with x plus 2 covered up. That gives us the value of b. And of course, we know that it ends up being that positive 3/5 from the previous example. But it just goes to show the cover-up method is really just a familiar strategy. A lot of students see this strategy when learning how to find those missing values. It's just nicer so that we can do so without as much work written down. Here we'll find the partial fraction decomposition for 6x all over 3x squared minus x minus 2. Here we're not so lucky as the last example. We do have to factor the denominator to get started. So we have 6x in the numerator. To get 3x squared, I'll need one factor with 3x, another factor with x to start with. And then to get -2 and then a negative x as the middle term, let's see, we're going to need 3x plus 2 and then x minus 1. This should check out, right? Outer is minus 3x, inner is plus 2x. So it's going to give us that -x. Okay, so we have distinct linear factors in the denominator. So each one is going to get its own partial fraction. So we're going to have some constant over 3x plus 2 plus some constant over x minus 1. And notice I'm not even bothering to put a value of a and b here because we're going to go straight into finding those values right away. Now, I don't have to start with the first partial fraction. I can start over here with the second partial fraction. The denominator x minus 1 has a nice value that's going to zero it out, just positive 1. Right? 1 minus 1 is 0. So I'm going to start by holding on to that value in my head of positive 1. And in this factored denominator version of the rational expression, I'm going to cross out or cover up the factor x minus 1. And then I'm going to substitute in positive 1 into each x. Now I am going to go ahead and do that using mental math. I'm not going to show any work here. 6 times 1 is 6, and then 3 times 1 plus 2 is 5. And so we're going to have 6 over 5 as the constant that goes above x minus 1. Now, let's go ahead and repeat the process, but this time to find the constant above 3x plus 2. This one is going to require us to deal with fractions, not too bad, but the value that's going to zero this out is -2/3. If I think about setting this equal to 0, I would subtract 2 and divide by 3. So -2/3 is the value I'm going to have to substitute in. So I'm going to come to this factored denominator version, and I'm going to cover up the 3x plus 2, and then I'm going to substitute in -2/3 into the remaining x's. All right, so this might be a little bit harder to do in our head, so it is okay if you need to do that scratch work off to the side. So I'm going to have 6 times -2/3 over -2/3 minus 1. Let's go right into making that 1 a 3 over 3, since we'll need common denominators to subtract these. Now, to simplify this, 3 divides into 6 twice. 2 times -2, that's -4. In the denominator here, let's see, if we add the opposite, we're going to have -5/3. All right, these are both negative, so we can make them both positive. And so if we multiply by the reciprocal, 4 times 3/5, we're going to have 12/5. So 12/5 is the numerator uh, of the partial fraction over here with a denominator of 3x plus 2. So while it did take a little bit of arithmetic, it wasn't too bad, and I definitely think it's shorter than some of the other traditional methods like solving a system of equations, or sort of creating this equation that we work with to find those missing values. We're going to try another cover-up method for this partial fraction decomposition. Here we have 3x over the quantity x plus 1 times the quantity x squared plus 2. The denominator is factored, but one of the factors is an irreducible quadratic, x squared plus 2. And so we're not going to completely be able to use just the cover-up method, but it is going to help us. And this is where we are going to need to know those other more traditional strategies. So here, let's go ahead and start by rewriting or writing out our partial fractions. So we'll have a constant a over the distinct linear factor x plus 1. And above the irreducible quadratic, x squared plus 2, we're going to have a generic linear expression. We're going to have bx plus c. So we're trying to find a, b, and c. We'll use the cover-up method to find the value of a pretty quickly. So I'm going to erase a because I'm just going to find it. If I think about what zeroes out x plus 1, that's going to be a -1. And so I'm going to come up to my original factor denominator expression. I'm going to cover up x plus 1, and I'm going to substitute in -1 into the remaining x's. So 3 times -1, that's -3. -1 squared, that's +1, plus 2, that's 3. So -3 over +3, that's -1. So we'll just go ahead and put a -1 there. But we're stuck finding b and c with more traditional methods. And so if you recall, with these partial fraction problems, we create the partial fraction and then we kind of want to put it back together. So here, if we put it back together, the common denominator will of course be the original denominator, x plus 1 times quantity x squared plus 2. And then the new numerator will be -1 times x squared plus 2 plus my bx plus c times x plus 1. All right, and now if the original rational expression is supposed to equal this new rational expression, their denominators are already equal. So what really we need to do is think about setting these numerators equal to one another and think about working with that equation to find the values of b and c. So in other words, we want to think about 3x being equal to -1 times x squared plus 2 plus this bx plus c times x plus 1. And we're trying to find b and c. So now, let's make a little bit of space here. Let's focus on just this equation for a moment. So we're saying the left side has to equal the right side. Well, the left side doesn't look like it has any x squared terms or any constant terms, but the right side has an x squared, and if we multiply it out, we would see it has constant terms. So the left side equation, we could express it as 0x squared plus 3x plus 0. And then the right-hand side, I am going to do some distributing. It's not too bad of a problem to do. So I'm going to have -x squared minus 2 plus bx squared plus bx plus cx plus c. So I distributed everything out. And the idea now is that I want to think about, all right, the stuff in front of x squared on the left, that's just 0, has to equal the stuff in front of x squared on the right-hand side. So what's in front of x squared on the right side of the equal sign? A -1 and a plus b. So what we do is we create a little system of equations here. We say 0 must equal -1 plus b. We found that by focusing on the x squared terms, right? And so we already found the value of a was -1, so that makes this equation just solvable right away, instead of creating more traditionally a system of equations. So we can just simply add the 1 to the other side, and we can say, perfect, b is equal to 1. Now, let's go ahead and try to find that value of c. So if I look on the right-hand side, I can see c twice. I'm going to focus on the fact that c is a constant over here on the right-hand side. So plus c, there's also the constant -2. So the constants on the right-hand side, -2 plus c, they must equal 0 because that's the constant on the left-hand side. So if I think about constants, that's what I focus on, whoops, then I get the equation 0 must equal -2 plus c. All right, well, again, because we already solved for that a value, this is just an equation that is solvable really quickly. Just add the 2 to the other side. So I get c equals 2. So I now have all the values of a, b, and c to finish off the problem. So what we have for our final partial fraction decomposition, we had -1 over x plus 1 plus bx plus c is going to look like x plus 2 over x squared plus 2. So our cover-up method did help us shorten our traditional work. And now let's try to use the cover-up method for this one, where we have x plus 1 all over the quantity x minus 3 times the quantity x plus 2 all squared. So what we have here is we have one distinct linear factor in the denominator, x minus 3, and then one repeated linear factor. So let's go ahead and set up our partial fractions and see what the cover-up method will get us. So above x minus 3 is going to be a generic constant. We'll call it a. So we have a over x minus 3. And then for repeated linear factors, what we're going to have to do is we're going to have a generic constant b over the linear factor to the first power, so x plus 2 to the first. And then we're going to have a generic constant c over the linear factor x plus 2 squared. So we create a partial fraction for each denominator that's repeated. Like, so we start with x plus 2 to the first, x plus 2 squared. If this was cubed, we'd have an x plus 2 cubed, and so on, right? So again, hopefully you're familiar with the general idea of how to set up partial fractions. So what can we do with the cover-up method here? What's that going to be able to find us? So it is going to be able to find us the value of a, so the value that is above the distinct linear factor. But how about these other two? Which one, if any, is the cover-up method going to help us with? It's going to help us with finding the last one, the one that has the repeated linear factor to the highest power. So we're going to be able to find both of these, a and c, but any of the lower powers from a repeated linear factor situation, we're going to have to go back to traditional methods. So let's go ahead and try to find a and c right away. So we'll think about 3 is what's going to zero this out. We'll go ahead and cover up x minus 3. If we substitute in 3 plus 1 is 4. And then 3 plus 2 is 5. 5 squared is 25. So we have 4 over 25. So wow, I mean, that's kind of nice to just get that out of the way, right? So we have 4 over 25. Okay, and now let's go ahead and try to find this value of c. So what's going to zero out x plus 2 is -2. And so if I cross out this x plus 2 squared, the entire factor squared, and I plug -2 into each remaining x, -2 plus 1, that's going to give me a 1. And then negative 2 minus 3, that's going to give me a negative 5. So negative 1 over negative 5 is a positive 1/5. So I have a positive 1/5 there. All right, but I didn't find the value of b. So what we're going to do is we're going to create. Now let's try the cover-up method for 2x plus 1 all over the quantity x minus 1 times the quantity x plus 2 squared. So we have a factor denominator, but we have a repeated linear factor. Let's go ahead and set up the partial fractions. So the first one is going to be a generic constant a over the distinct linear factor x minus 1. And then the repeated linear factor x plus 2 squared, we're going to have a generic constant, let's say b, over x plus 2 to the first. And then we keep going with partial fractions with a generic constant on top and the linear factor x plus 2 to the next highest power, so that's going to be squared, until we reach the repeated exponent. So we did already. So we had x plus 2 to the first and then x plus 2 squared. So here we're trying to find the values of a, b, and c. What is the cover-up method going to allow us to find using some quicker mental math? So it is going to allow us to find the value of a, so the value above the distinct linear factor. And it is going to allow us to find the value of c. So if you look at the original factor denominator, we have x plus 2 squared, and c is above exactly that, x plus 2 squared. So that's what the cover-up method is going to be able to allow us to find when it comes to repeated linear factors, the repeated linear factor to the highest power. Any of the smaller ones, we're going to have to go back to the traditional methods. So we're going to be able to find the value above x minus 1. So I'll erase that so we can fill it in. And then the value above x plus 2 all squared. Let's try to do some mental math here. For x minus 1, we're going to have the value x equals 1 in our head to plug in after covering up our x minus 1 factor. If we plug in 1, 2 times 1 plus 1 is 3. And then 2 plus 1 is 3. And 3 squared is 9. So we're going to have 3 over 9. That simplifies to 1/3. So we're going to have 1/3 above x minus 1. And then to find the value of c, we're going to substitute in negative 2 into everything except what we're going to cover up. We're going to cover up x plus 2 squared. So if we plug in a negative 2, 2 times negative 2, that's negative 4, plus 1. So the top's going to be negative 3. And then on the bottom, we're going to have negative 2 minus 1. Well, that's also negative 3. So negative 3 over negative 3 is 1. All right, so now we just need to go ahead and find the value of b. So we'll go ahead and figure out what's that primary equation. And I'm going to skip kind of that step with showing the entire common denominator. We're going to go to that primary equation. Again, I really encourage you to make sure you go back and review the traditional methods if this is going a little too fast for you. So the original numerator, 2x plus 1, must be equal to this numerator here that comes from, putting all these fractions back together. So in other words, over here, 1/3, that numerator would have to be multiplied by x plus 2 squared. So my x plus 2 squared factor would have to be multiplied by 1/3. Now, in terms of this middle partial fraction, the numerator b would have to get multiplied by 1 copy of x minus 1 and 1 copy of x plus 2. So b times x minus 1, and then x plus 2. And then this last numerator, 1, the only thing it's missing is x minus 1. And so we're going to have plus 1 times x minus 1. So this is going to be our primary equation. Again, the idea is that it's technically over that original denominator, x minus 1, x plus 2 squared, right? They're both over that same denominator, that sort of quotes. But we can skip that, right? We're just focusing on setting the numerators equal to each other. Now, from here, we have some options actually. We're only missing one value. We're just missing the value of b. So while we can kind of start to set up a system of equations, here's another thing we can do. If this left side is truly equal to this right side, that should be true for any value of x that we choose, including letting x equal 0. So here's yet another technique. We can go ahead and just let x equal 0, and the only thing that will be missing is our value of b. So if I let x equal 0, on the left side I'm just going to have 1. Right here, 0 plus 2, that's 2. 2 squared is 4. So 4 times a third is 4 thirds. Plus, now right here, 0 minus 1 and 0 plus 2, negative 1 times 2, that's negative 2. So what I actually should have done is put minus. So we have minus 2b. And if I plug in a 0 into this x, 1 times negative 1 is a minus 1. So I have this basically linear equation that I can go ahead and solve for b for. So here, I'll go ahead and create a little bit of space. I would say, okay, 4 thirds minus 1, that's 1 third. So I have 1 equals 1 third minus 2b. If I subtract 1 third to the other side, I have 2 thirds is equal to negative 2b. If I divide both sides by negative 2, or really that's like multiplying by negative 1/2, then these 2's cancel and I get b is equal to negative 1 third. So what is my partial fraction decomposition going to be? I'm just going to come back up here and erase b and turn it into negative 1 third. So there is my final answer. And we did use the cover-up method to at least find the values of a and c that corresponded to the pieces, the factors that were involved in the original rational expression.